Today we'll start our introduction to probability. Let's start with some definitions. First thing we need to talk about is an experiment. An experiment is just the observation of a random phenomenon. An outcome is any result of an experiment. The sample space is the set of all outcomes of the experiment, and an event is a set of outcomes of an experiment. So let's take an example. I could do an experiment of rolling a set of dice. The outcomes would be the number of dots observed on the dice. An event could be getting doubles. First type of probability we'll talk about is called empirical. The empirical probability of an event is the number of times an event occurred divided by the number of times the experiment was conducted. Here's our notation. So P for probability, and then I have parentheses around E. Notice E is my event, but it's also a set. So think back to when we did sets in this class, maybe way at the beginning. The same kind of thing here. So when I now find the P of E, which is the probability of E, I look at the number of times E occurred, so it's like N of E, over the number of times the experiment was conducted. So let's take an example, and we're going to kind of work through this example a while. Let's flip a coin once. If the coin lands on head, then the probability of heads is 1 over 1, which is 1. So if I got heads by flipping a coin once, then what would be the probability of getting tails? It would have been 0. Here's this difference between what I would call theoretical, and not just me, anybody would call theoretical probability and empirical probability. Theoretical is what you think will happen, and in your head you're probably thinking, if flip a coin I got a 50% chance of getting ahead. But empirical is from really doing the experiment, and then in really doing the experiment I did get ahead, so 100% chance I got ahead, 0% chance I got tails. So what needs to happen is I need to repeat an experiment. So the table on the right shows the results of flipping the coin a total of 5 times. So you can see I numbered my flips, flip 1, 2, 3, 4, 5, and then the outcome, and I had head, head, tail, head, tail. All right. On the farthest column, I gave you the probability of getting ahead. So with one flip, getting ahead is 1 out of 1, one head out of 1 experiment. I flipped it again, and I got ahead. So now 2 times I got ahead out of 2 experiments. On the third time, I got tails. So 2 heads out of 3 flips. On the fourth time, I got ahead, so this is 3 heads out of 4 flips. And then last one, tails, says 3 heads out of 5 flips, right? So anytime we're doing empirical means we have real results, real experiments, not just what we think should happen. So here's Bernoulli's law, which is also called the law of large numbers. It says an experiment needs to be repeated a large number of times to arrive at the event's probability. This is like our coin toss. We can't flip a coin once to find the probability of heads. We need to repeat the experiment a large number of times to find the true probability. With experiments like flipping a coin, we expect that eventually the probability will reach 1/2, but in other experiments, we don't know what the real probability of an event will be. Consider a new medication. Scientists don't know the result of giving a patient a new drug until the drug has been tested. Tested on a few people would not be adequate to predict the results of the drug. They need a large sample of people to be able to actually report the results of the drug. So here's just a small one, or a small study you can read over on the left. It says a Prilosec Study, and I just took a piece of it to show you that the information shows the clinical study of Prilosec that involved 3,096 people. This number of participants helps the company better predict how patients will react to the medication. So our thought should be when someone's doing a drug test, we don't want them to test 5 or 10 people. We want it to be a very large number of people so they can see all the different outcomes that occur. That creates our sample space. And then how often they occur tells them the probability that a good reaction will happen or a poor reaction will happen. So let's consider rolling a die. I wanted to give you something with a larger number of outcomes. So we started with flipping a coin where there are only 2 outcomes. Now that I switched to rolling a die, I have 6 possible outcomes. So here I said a single die was rolled 10 times and the results are in the chart. So I gave you the results, 1, 2, 3, 4, 5, 6. These are would be the dots on the die, and then how often it occurred is in the next column. So you can see here that if I wanted to talk about the probability of getting a 6, I would look at the 6 and say it happened 3 times. So 3 out of 10 times says the 6 occurred 30%. Similarly, I could look at the probability of a 4. So here's the 4. It happened 1 time out of my 10 throws, so that says the probability of a 4 would be 10%. What if I increase the number of rolls? So here I made the number of rolls 50 more, which gives me a total of 60 rolls altogether. And let's go back to those numbers. Now when I look at the 6 on the bottom, there are 14 times that a 6 came out of the 60 rolls, which gives me 23%. The probability of getting a 4, so now I look at the 4, which now says there were 8 times that it happened, is 8 out of 60 is 13%. The more the die is rolled, the more even the results would become. Eventually, you would think that because 1, 2, 3, 4, 5, 6, there shouldn't be any tendency to something happening more than others, that they should all end up having close to the same frequency if I were to repeat this a bigger number of times. So here I want you to try. I gave you a survey of 500 people, revealed the number that owned a dog. If a person is selected from the group at random, I want you to first find the probability the person does not have a dog. Then I want you to look at the probability that the person has exactly 1 dog. And the last one, I want you to find the probability that the person has less than 3 dogs. When you find your answers, you can either write them as fractions in reduced form, or you can change it over to a percent. I would say stop, give yourself a few minutes to do this, and then come back and check because I have the answers on the next slide. Alright, so here's what I have. Part A, I wanted the probability the person does not have a dog. So that was our first column, 0 dogs owned. That was 320 people, so 320 over 500 reduces to 16 over 25, or 64%. For part B, I said find the probability the person has exactly 1 dog, so that word exactly is really important. So I'm not looking at any having more than 2 dogs, only the 1 dog. So I had 125 people out of the 500 people surveyed, so that says 1/4 or 25%. And the last one says find the probability the person has less than 3 dogs. So less than 3 could be 2, 1, or 0. So I added the 320, the 125, and the 40. Which gave me 485 out of 500. I reduced that to 97 over 100, or 97%.